Number 13, given the function f of x equals x minus 6 over x squared minus 2x minus 24, for what value of x does the function have removable discontinuity? For what value does it have an infinite discontinuity? So I'll do the algebra first, but this algebra is going to be new to you because I haven't really taught it. But basically what we're doing here is, if you remember the very first lesson we covered, which was 0-3, we talked about factoring. This is a trick for factoring. What you're not allowed to do in mathematics is cancel terms. So I can't say this is a term and it cancels with this term down here. That's not accurate. You cannot cancel terms. But what you can do is you can factor this. So I'm going to factor that using the x method, because it's a trinomial, and I'll say I'm going to put the product of a times c on the top. And remember, this is like my a here. That's my b. That's my c. So 1 times negative 24 is negative 24. And the b goes down here. Now I'm going to look for two numbers that multiply to be the top and add to be the bottom. Now you could do plus or minus 1 and 24, one of these being negative to get negative 24, but you'll never get negative 2 when you add or subtract those. So I'll move on to the next number. You could try 2 and 12, but again, 2 and 12, you cannot add or subtract 2 and 12 to get negative 2. So I keep moving on. And basically I want to sometime come to 4 and 6. 3 and 8 wouldn't work, but now I get to 4 and 6, and I can see they are 2 apart. I need this to be negative 2. So that's negative 2, or negative 6 rather. 4 minus 6 is negative 2. And multiply, that does give me negative 24. So these are my values. So this means my equation, I could rewrite it as being f of x equals x minus 6 stays on the numerator. But in the denominator, I'm going to split my a. So let me come over here. Split the power of a, so that splits apart. So instead of being 1x squared, it becomes 1x. So I have 1x, or just simply x, plus 4, and I also have x minus 6. The 4 and the negative 6 come from there. The x's are just this split. Now as I look at this function, I can see something happens. Now I have identical factors. Though earlier we could not cancel terms, you are allowed to cancel factors. This factor up top and the numerator will simplify with this factor in the denominator. They cancel out, or they get removed. That is removable discontinuity. So this has, f of x has removable discontinuity. And I'm about to show you all this in the graph. When x equals 6. And the way I get x equals 6 is because x minus 6, you'd set it equal to 0, and then you would add the 6 over. That's where that value came from for that. Now, so it has a removable discontinuity when x equals 6. Now, this thing is down here in the denominator. And if you remember in mathematics, you're never allowed to divide by 0, which at this time would be 1, since everything in the numerator is canceled out, just 1's left over. 1 divided by this, but you're never allowed to divide by 0. In math, that's a problem. So since this is infinitely down the bottom, we can't cancel it out. Like this we removed, hence removable. This is infinitely down there. I cannot remove it. It's down there forever. So that's going to be the infinite discontinuity. So I solve for that value, x plus 4. It cannot equal 0. So when x equals negative 4, we have problems because we'd be dividing by 0. Negative 4 plus 4 would be 0. And you're not allowed to go 1 divided by 0. So that's my infinite discontinuity. F of x has an infinite discontinuity when x equals negative 4. And that would be my answer here. Now, I did all this algebraically. But as it concerns our class up to this time, we've really been dealing more with the graph. So let's go look at this in the graph, the original equation, and see how we could have determined this. So if I go in to a graph here, my numerator, so to get a fraction first, we hit Control Divide. In the numerator, we have x minus 6. In the denominator, we had x squared minus 2x minus 24. Now I graph it, and this is the infinite discontinuity, and we'll see the other value in a second. Let me go here, and get the other one. We set at 6 and -4 were our values. I'm going to get this value real quick. All right, and I'll come back over here and paste them. Okay, now that I have these graphs, check this out. The infinite discontinuity is in green here, so I'll put it in green. When you graph it at -4, this graph breaks and goes to infinity on both sides. That's why it's an infinite discontinuity. That was at -4, -1, 2, 3, 4. That's where that's located. That removable discontinuity happened when x equaled 6. This said here, x equals 6 is undefined. That means at 1, 2, 3, 4, 5, 6, we should have an open circle right there. And the same over here, 1, 2, 3, 4, 5, 6. You would have an open circle right there. So that's how you would have your infinite discontinuity, and you would have your removable discontinuity. Those values being x equals -4 and x equals 6, respectively.